Okay, so good morning, everyone. I'm Manjavacas. I come from the University of Granada, and I work in the IFMIF DONES Spain project. A little words about me.
First has always to be
Okay, perfect, thank you. So a little words about me. I'm a PhD fellow at the University of Granada and the IFMIF DONES project. And my thesis is titled Deep Reinforcement Learning for Genetic Design of Safety Elements in IFMIF DONES. I'm a member of the Sustainable Artificial Intelligence Lab there in the University of Granada. And well, our research mainly addresses reinforcement learning problems for building energy optimization, HVAC control. Check out our project, Synergy, which is quite cool. We also do physics-based models for power prediction and grid operation with reinforcement learning. So let's talk about fusion energy. As you should know, we are trying to apply fusion energy in a commercial way. And maybe the biggest step towards fusion energy in Europe is nowadays ITER, the fusion tokamak reactor that is being built in France, and which is expected to start working in the early 30s of this century. As you can see here, it consists of a tokamak reactor which contains plasma inside, and well, it's a very huge facility. ITER, the International Thermonuclear Experimental Reactor, will be a first step towards DEMO, the demonstration power plant, which will be the first commercial fusion reactor that we will have here in Europe. But the problem with these kind of reactors is that the extreme conditions that happen inside this toroid, this tokamak, make quite challenging to choose the different materials to be used in their construction. So in the early 90s, the material scientific community promoted the development of a neutron source for the qualifications of materials to be used in future fusion reactors, such as DEMO. And in this irradiation facility, material samples will be exposed to fusion-like conditions. So here we have IFMIF DONES, the International Fusion Materials Irradiation Facility, demo-oriented neutron source. So IFMIF DONES, this building, will include a deuterium linear accelerator in its first phase, and in its second phase, one upgraded to IFMIF. It will include two deuterium linear accelerators. It is being built in Granada, in Spain, and it's an Eurofusion project, and it's part of the Fusion for Energy program. So several partners are involved here. The main partners are Spain and Croatia. It's a joint collaboration, but several countries all around Europe are also collaborating, even Japan, and it's expected to start working in the early 30s. So particle accelerators are great, but we have to build them somewhere, ensuring safety conditions and in an efficient way. So here is the tricky part of particle accelerators, the IFMIF DONES project, well, it will entail a critical infrastructure where safety systems and protocols have to be ensured. For example, in this facility, we consider accidents related to potential tritium releases, which is, if you don't know, toxic for people, radiation doses, amplifiers. So several safety measures are being implemented in this facility: the treatation systems, inertized rooms, or purification and control evacuation of gases to the environment. So we will focus on the dynamic confinement part of the system. So what is dynamic confinement? Dynamic confinement is a safety measure that we implement in this kind of facilities, in radiological nuclear facilities, and which may consist on maintaining different pressures in different rooms. So in case of an accident or some kind of hazardous spread of any substance, these potential hazardous gases keep contained in their respective enclosures. So as you can see here in this preliminary design of the DONES facility, we have some green rooms in this building plan, which correspond to C2 confinement class. Then we have the orange and yellow rooms, which is a C3 classification, and C4, the most critical rooms, which are in the lowest level pressure. So in case of an accident, everything remains in the corresponding room. So the system which is in charge of ensuring these stable pressures is the heating, ventilation, and air conditioning system. The main functions of this system is the dissipation of gases with non-radiological risk and ensuring stable pressures inside the building. So the general schema of this system is the following. We have several air handling units which provide air to the different rooms, and depending on the classification of the rooms, we have several filtering stages and vitrification measures prior to the release of the gases to the environment. And the general schema for each room is the following. We have some inlet and outlet leaks for each room because of the pressure differentials and because rooms are not completely tight. And we also have HVAC supply and exhaust flow rates that ensure these stable pressures inside the different rooms. So my work as a member of this project is developing simulation models of the building in order to analyze how these pressures are going to be maintained and how it's going to be done in an efficient way. So we are using Melcor, which I don't know if you know it, but it's a well-known computer code that is mainly used for in nuclear and radiological facilities, mainly for assessing accidental scenarios. And the interesting point here is that HVAC design decisions in our simulation model will match the design decisions in the real scenario, in the real world. So we are trying to assess different design decisions in this model and then trying to translate it to the real system. And here is where deep reinforcement learning plays a fundamental role. As you know, deep reinforcement learning has emerged as an outstanding competitor to conventional control methods. For example, HVAC control in residential buildings, particle accelerators, or even the fusion domain with the tokamak plasma control and so on. So I'm developing Melgym, which is a gymnasium environment that allows continuous control in Melcor simulations. And as I mentioned, our final objective is to simulate and validate different HVAC system design alternatives. So, as you remember from this schema, we have the supply, the exhaust, and several inlet and outlet leaks for each room. The fact here is that leaks are not controllable and depends on the pressure differentials between adjacent rooms, and the HVAC exhaust flow rates are imposed in order to ensure a certain quantity of renovations per hour for safety measures. So the only controllable part of our system is this HVAC supply flow rate. So we propose the following MDP, where our agent interacts with a Melcor simulation over a building model. The observations here are the current room pressures of the building. The actions are the HVAC air inlet flow rates. The reward is the proximity, the sum proximity to target pressure values of each room. And its transition performed here is a Melcor simulation during a certain period of time. So this is a more detailed diagram where we can see that at each time step we perform a Melcor simulation, and the state of the simulation is stored in some kind of temporal file. We call it restart file, which allows a warm start from the previous state of the simulation in the next agent interaction. So some preliminary results. We have now several initial air inlets estimation. We also plan to simulate accidental scenarios over this Melcor model. Here you have part of this model corresponding to an HVAC branch. And for example, here you can see the performance of a TD3 agent controlling the pressures of a small group of rooms. We will have several rooms. These are some of them. The final objective here is to estimate the HVAC power consumption of the building and trying to optimize it while maintaining this pressure equilibrium, and also to evaluate the different leak rates in critical rooms. We want to calculate the permissive leak rates that will allow us, well, to make like to propose several solutions to the dynamic confinement problem and check which of them is more viable than the others. So thank you very much for your attention, and if you have any questions, don't hesitate to ask. Thank you.
Thanks a lot, Antonio. Are there any questions?
Very interesting. So we have a group at CERN, industrial controls group that was actually looking at some methods, but they didn't use reinforcement learning. They stayed with MPC and then learned the policy actually directly from the MPC that they thought that they had full control. But their worry was that having formal methods to make absolutely sure that this is robust in the all conditions. So what do you think? I mean, if you are successful in the end, do you think you'll be easily able to apply this, or what is the procedure to be able to make sure that this is fully robust under
well,
circumstances?
I have to say that this is a very preliminary project, so we are trying to go step by step. This is like a preliminary vision of how these deep reinforcement learning agents could be applied in the real system, but of course we are quite far from implementing them. Of course, there are several design decisions that are still that we should evaluate in future phases of the project. But well, as soon as we have a complete simulation model of the system, we can start exploring these control systems. And as you know, sometimes it's very complicated to test these systems in real scenarios and critical infrastructure. But well, it's an alternative, and we have to explore this possibility, and it's quite promising. So why not? Let's try to do it, or at least it will help us to evaluate the different design proposals for this system. So at the end, it will have some repercussion in the real system.
How difficult is it to try it in the real system?
Try to?
How difficult is it to try it in the real system?
It's very difficult. Well, at least, well, first we need the building to be constructed. Okay. It's under construction. But well, our mission as researchers is to propose some solutions to future problems that we know that will arise. And as I mentioned, it is always it is already being used to assess the future designs of the system. So at least it has some utility, and we want to explore it in the next stages of the project.
What are the time scale of events in these HVAC systems?
Well, we are now considering an action applied over the Melco simulation in time periods of 15 minutes. But well, we also have the internal time that is managed by the Melco simulation, which are very computing expensive simulations. So maybe we need like 1 hour simulation for a quite small problem. Let's see, one of our main problems when addressing this kind of control system in such a precise way.
You mentioned that there are leaks in the room, for example.
Yes.
Is it a goal to detect that the leak is increasing, for example? Or?
Yes, one of the advantages of using Melco is that it allows the continuous monitoring of the concentration of gases in the different rooms. These leaks are common, and every room in every building has different leaks. Of course, in a facility of these characteristics, these leaks sometimes are not permissible, so we use metallic liners to involve this kind of rules, but they are not always completely tight. So we have to consider that at least a small amount of hourly leak rate is considered. There are several standards that address that in radiological facilities also.
So in the future, do you imagine like a central policy controlling all of the rooms, or each room has like a separate control?
No, the objective is to have a central policy, because if each room acts independently, it's very complicated because we have a lot of rooms, and well, you cannot address the control of one room independently of the other room, the adjacent rooms, because they are all dependent. Maybe with a multi-agent proposal, but that's quite complicated. So we always think about a single policy that is common for the building.
Yeah. So in these systems of gases, I mean, there's a latency, there's some sort of inertia, so it's like you have an action and you have to wait a certain amount of time too. So is this taken into account in the simulation and in the design?
Yes, one of the things that we have to consider here is that all the rewards are delayed, but it happens in general with every building control. For example, if you control the temperature of a building, there is some period of time between your action and the expected behavior of the system. But at the end, the agent should learn to predict these dynamics and apply actions with some prevention of the possible consequences.
Yeah. Referring to the other question of Cameron, how high dimensional is this problem? So how many rooms do you have for this goal?
I don't remember the exact number, but around 50 rooms.
50.
So it's a high dimensional problem. But the good thing here is that the actions are not individual for each room, because several rooms share the same air inlet. So the system is divided in several branches, and we have the control over that branches, but not the control for the individual inlet for each room. So maybe the actions are 12 actions, 18 actions, something like that.
Okay. And do you consider in your simulation external influences like the weather or?
Currently not, because we are only dealing with pressures. Well, we also consider the leaks to the environment, which is at atmospheric pressure. But when we add the temperature variable, which is something we are planning to include, we should consider external temperature, and well, that will complicate the problem a little bit, but that's our view.
Any more questions?